We learned something about the limit. We also learned something very important, the epsilon delta formal definition of a limit, and we learned how to play with it. Now, we're going to learn some properties of limit. And there are several rules or several theorems that I hope that you would know, okay? So the first one is this. We call this is Theorem 1.1. Okay, that's something about the basic limits. So if I write it, you can see the limit x approaches to c of b equals b. Okay, c is a number, b is a number. So the limit of b, which is like a constant function, is like a y or f of x equals b. F of x equals 5. So limit when x approaches to c, it doesn't really matter. It just the answer or the limit is just the b, right? The other one, limit when x approaches to c, then x will be just c. Okay, so this two quite obvious, isn't it? And the third one, limit x approach to c and x to the nth power. In this case, n is a positive integer, like a 1, 2, 3, 4, 5. And that is just c to the n. Okay, so for example, I get a limit x approaches to 5, 8 is just 8. Okay, because 8, the limit of 8 is just 8 when x approaches to whatever. And this when x approaches to 5, x. When x approaches to 5, then that x would be just, the limit will be just 5. Okay, the third one, when x approaches to 5, 5 to the third. And that, x to the third, x to the third. Okay, so that would be just a 5 to the third, which is 125. All right, so those, do you think that's obvious? I think so too. All right, now this is the first theorem. Now let's work on the second one. I'm gonna change a pen. This one works better. Theorem 1.2. 1.2 is about the properties of the limit. Okay, sorry, I gotta turn something off. Okay, those are this. If I give you the limit when x approaches to c, f of x equals L, and also I give you limit x approaches to c, another function, let's just call that g, and that equals k. So when x approaches to c, f of x has the limit L, and a g of x has the limit of k. Then here we get several things. Number one, limit x approach to c, b times f of x, this guy, will be just b times L. Okay, so when x approaches to c, there's a constant multiplied by a function, and that's just that constant multiplied by the function, the limit of that function. For example, limit x approach to c, and we know this limit x approach to 5, x squared equals 25, right? That's what we did a while ago. So what about when x approaches to 5? Then 2x squared. If we know this x squared approaches to 25, then 2 of that will be just 2 times 25. That will be 50. It's not too bad, isn't it? Okay, number 2. Limit x approach to c, and we have f of x plus or minus g of x Remember, this one has the limit L, this one has the limit K. So that will be just L plus minus K. Now, I give it this. All right, I give you another one, g of x, which is a limit. That x has to approach to the same number. All right, and this one is x plus 1. And that would be 5 plus 1, that's a 6, right? That's what we know earlier. So which means limit when x approaches to 5, what is 2x squared plus x plus 1? See, f plus g. And then that would be this limit, which is a 50, plus this limit, 6. So the answer is a 56. So that's a property, addition and a subtraction, okay, or sum or difference. Number 3, product. When x approaches to c, f of x times g of x, the product will be just L multiplied by K. Okay, very similar. We go limit x approaches to 5, and our L is x squared multiplied by K is x plus 1. Okay, then this limit will be 25 multiplied by 6. So that is 150. Okay. Oh, here I put a 2x. So I already doubled that. Okay. Anyway, so that's number 3. And then number 4, limit x approach to c. We have f over g. That will be just L over K. And in this case, that K cannot be 0. So I will continue. I will give you one quick example. When x approaches to 5, x squared over x plus 1. This will be the x approach to 5. The top is 25. The bottom is 6. Okay? Of course, you can say 4 and 1/6. It doesn't matter. So that's number 4. And number 5, limit x approaches to c, f of x to nth power. And that would be just L to nth power. Okay? So limit x approaches to 5. And f of x is x squared, right? So let me just square it again. And that would be the square of this, the limit of that is 25 and then square. So there'll be 625. So those are the 5 properties. Those are the 5 properties, and then I give you some examples. So that's my theorem number 2. So far, I think the 1 and the 2 looks very, very obvious, right? It's not hard at all. So shall we go to the next one? The theorem 1.3. Okay, so when p limit x approach to c of f of x equals f of c, f is a polynomial function. For polynomial function, you can just use direct substitution method. Okay, and if for polynomial, for rational, so if you have x approach to c, you have a p of x over q of x. Then you can just go limit x approach to c, p of x. That's what we know from the previous theorem 1.2. Okay, so q of x. And that, because both are polynomial, this is a rational, so this is a polynomial. Therefore, you're going to have P of C over Q of C. So this is for the rational function. Looks like a fraction. Both numerators and both numerator and denominator are polynomials. So this is 1.3. Okay, so I think I should give you one example. Now, f of x f of x equals x squared minus 2x plus 1. This is f of x. Sorry, I should write like that. Okay, so what is f of x limit x approach to 5? I like 5 a lot, isn't it? This is f of x is a polynomial function, so the limit of f of x as x approaches to 5 just equals f of 5. Therefore, it's going to be 5 squared minus 2 times 5 plus 1. So which is 25 minus 10 plus 1. So my answer is 16. That's your answer. Okay, so what about this one? I give you another one. G of x equals, not that, okay, it's x, let's say just x, okay. Is that easy? No, it's a g plus 2. I made that up. So limit when x approaches to 5, g of x will be g of 5, which is g of 5, that's a 5 plus 2, that will be 7. Now, I give you a rational. X approach to 5. I give you this. X squared minus 2x plus 1 over x plus 2. Make it complicated. It looks complicated, but it's not really, because that's a rational function, and both the numerator and the denominator, they are rational. Sorry, they are polynomials. So we just substitute that. So I'm going to substitute x approach to 5 to top. So I get a 5 squared minus 2 times 5 plus 1. Okay, and I know that's a 16. And the denominator is a 5 plus 2, which is a 7. So the answer will be 2 and the 2 over 7. So that's my answer. So you see from this, we have a polynomial function. Then it's very easy when we go to the to find the limit, which is use the direct substitution method. If you have a rational function and the denominator is not a 0 at that point, at that like what x approach to that point 5, and that g of x, see, did you notice that g of x is not a 0? G of c is not a 0, right? G of c is not 0. Then again, if you have a rational function, if that x approach to 5 when x equals 5 does not make the denominator 0, then you can just go ahead and use the substitution method. So this is 1.3. Are we ready for 1.4? It's going to be a radical function. F, it's a radical function. What is radical function? Like a square root. Okay, square root, cube root. Okay, and that looks like this. Okay, so let n be a positive integer. N positive integer. N is a positive integer. Okay, this limit. Again, x approach to this number c. The nth root of x will be just the nth root of c. Okay, so that, first of all, we have to make sure that this is a valid. If you, for example, if you have n is a square, 2, so the square root you're not going to take a negative number, right? And then take square root of a negative number. So make sure that this has to have the definition. So which means this limit is valid for c when n is odd, and it's valid when c is greater than 0. So we ask c to be 0, and then that is the radical function. Are we using the direct substitution method? Yes, we are. We just substitute c here. Okay, so this one, I don't need to give you any example because this is so easy, so straightforward. So that's 1.4. We get more. 1.5. Theorem 1.5. What is a composite function? Composite function is f of g of x, right? Okay, so limit x approach to c, f of g of x. That will be f of limit x approach to c, g of x. Here. And if a g of x is, for example, if the limit x approach to c, g of x equals k, okay, then that will be f of k. So you just substitute k into that f, then you can get it. So f and g are the functions such that we have this limit, g has a limit, and then this limit of this f of x when x approaches to k, f is defined, that has a limit, then we have this. All right, so let me give you one example. Find the limit x approaches to 0, square root of x squared plus 9. So here is square root of a polynomial. So my f is a square root function. This g of x is actually x squared plus 9. All right. So by definition, and this we can just use the substitution method, put it in. So it's going to be 0 squared plus 9, and that would be root of 9. So the answer is 3. It's very easy, right? Really straightforward, but you have to make sure, remember, you have to make sure that this x squared plus 9, it is in the domain for this function. So that 9 is in the domain of the function of f, which is a square root. So yes, x squared plus 9 is positive, so that is valid. All right, so we're going to do another one. We're going to do limit x approaches to 5. I don't know why I like 5 so much. Okay, so cube root of 4x squared minus 19. Substitution. Cube root, that's my f. 4x squared minus 19, that's my g. So I just substitute. I get the cube root of 4 times 5 squared minus 19, which is cube root of 5 squared is 25. 4 times that is 100. Minus 19 is 81. So cube root of 81. And 81, we can have a complete cube, which is 27, right? Remember, 81 is 27 times 3. So that 27 comes out of this cube root sign, which is 3, and then cube root of 3. Now you realize I like 3 a lot. So that's your answer for this one. So this is the composite functions. Okay. Again, we're using direct substitution method. So theorem 1.6. Now, it's getting harder, okay? This is the limits of trigonometric functions. So I try to scare you. X approach to c, sine x, which is sine c. Okay, limit x approach to c cosine x is just cosine c, limit of sine cosine. Now the next one, okay. The next one will be tangent x approach to c, tangent x, that will be tangent c. Again, you're gonna say, wait a minute, are you doing direct substitution again? I am. Tangent is, some book says COT, someone says CTG. It's the same thing. Okay, so it's as long as you understand, that's okay. And the sine, cosine, tangent, cotangent, the last two is secant and cosecant. So limit x approach to c, secant x, that will be secant c, and the limit x approach to c cosecant x, that would be cosecant c. Trigonometric, again, direct substitute. There's really nothing too hard. For example, what is the limit when x approach to 0 sine x? And that would just be sine 0, which is 0, isn't it? What about this? What about limit x approach to pi? Okay, and x times cosine x. That would be, because this is the limit of a product, so it's going to be the limit x approach to pi, the first, multiplied by the second limit x approach to pi cosine x. And when x approach to pi, limit of x is just pi, and then determine when x approach to pi, this is cosine pi. See, we're using the one of the property we did earlier, 1.2, and also we use the trigonometric, which is 1.6. You don't have to remember the number. You don't have to tell me that is 1.1 or 1.5 or 1.6. No, you don't really need to. As long as you know how to do it, you're okay. So what is cosine pi? Cosine pi is -1. Therefore, this is -pi. That's your answer. Okay? All right? So the last one. What is the limit when x approaches to pi over 4 tangent square x? That will be tangent square pi over 4, or it's actually is a tangent of pi over 4 square, right? What is a tangent of pi over 4? Pi over 4 is like a 45 degree. That tangent is 1, so it's 1 square, which is 1. That's your answer. Okay, so I give you the examples to show the limit of this trigonometric functions. All right, now the last one is important. Well, it's interesting. I think it's interesting. Theorem 1.7. So you have this f function. You have a g function. These two are the same. So f of x is equal to g of x, except at x equals c. So that means only when x equals c, when x is exactly at that point, f and g, they're different. Everything else, they are the same. Then limit f of x approach to c, limit, I don't have to write that, right, will be the same as limit x approach to c, g of x. Ooh, it says there are two functions, they agree with each other, or they're the same except at particular point. And then, but then they do have the same limit. It was like, remember, we have a line and then another line, another function, we just cross this point out. So see, they have the same limit, isn't it? I give you an interesting example here. How do I use this? When x approaches to 2, and the denominator is x minus 2, and the numerator is x square plus x minus 6. This is a function. That's my f of x here. F of x, that's f of, it's not. F of, let me simplify that, okay? So I can factor this guy because, look, I cannot use a direct substitution method because if I put in x equals 2, 2 minus 2, I get a 0 in the denominator. The numerator, I get a 2 squared, which is a 4, plus 2, which is a 6, minus a 6 is also 2. So I cannot use the direct substitution method. But I know how to factor this. Now look, x squared plus x minus 6. Isn't it just x plus 3 times x minus 2? Right? Now, if you do x squared plus x minus 6 divided by x minus 2, you get x plus 3. Okay, so f of x is actually this x squared plus x minus 6 over x minus 2. And your g of x is just x plus 3. These two are exactly the same except at this one, x cannot be 2, except at x equals 2, because when x equals 2, f is not defined. This function cannot be defined when x equals 2, but this one is okay because that's just a linear function. So these two agree with each other except at this moment. Therefore, the limit x approaches to 2 of f, which is x squared plus x minus 6 over x minus 2, will be the same as x approaches to 2 of x plus 3. Now, life is easy because you just plug in there, you get a 5. Okay, so did you notice that if you want to do this, then you have to know how to do factor? And also, if you plug in x equals whatever number here, in this case is 2, whatever, when you put x equals 2, put that in the numerator and denominator, you get a 0 on top, 0 on bottom. What does that mean? That means they both can factor out x minus 2, and then you can just simplify this expression. So you make a g, you get a g, and this f and a g are the same except at that point, at that moment, when and make both numerator and denominator to be 0. All right, I give you another example. I think just one more. Find the limit x approach to 5. Again, see, I like 5 a lot. So I get x squared minus 25, and I get x minus 5. So this is also very similar to the one we did earlier. You plug in 5 here, you get a 0. You plug in 5 here, you get a 0. And so you cannot do that, okay? So you cannot simplify that easy. You cannot just direct plug in. However, that x squared minus 25 divided by x minus 5, you can factor the top. You get x plus 5, x minus 5, and the denominator is x minus 5. When x minus 5 is now 0, of course, you put that in the denominator, it cannot be 0, so you cross it out, it becomes x plus 5. I don't really need the parentheses. Okay, so therefore, this one is going to go from here to here. So x approach to 5, x squared minus 25 over x minus 5. I simplify that by factor the top and the cross out with the denominator. I get x plus 5. And the answer, 5 in directed substitution. So I get a 5 plus 5. The answer is 10. Okay, if you don't trust me, what you can do is you can make a little table that goes back to our earlier session that x approach to 5. So you go 5.1, then 5.01, 5.001. On the other side, on the left side, you go 4.9, 4.99, 4.99. You can try that too. But anyway, by this theorem 1.7, and then we can just use the direct substitution method, and then we can get it. Okay, so now we're going to think about all the theorems that we learned for the property, right? Okay, what was the first property? I don't know whether you still remember. The first property is a very special case. A constant, still the constant, doesn't matter about x. The limit x approach to c of x, that will be c. And if n is a positive integer, then x to the nth power will be, that limit is going to be c to the nth power. Direct substitute. Okay. Now, theorem 2 is a complicated talk about this scalar, see, it's a scaled, right? Scale multiplication. And this is the sum and difference between two functions. And this is the product of two functions. And this is the quotient of two functions. And here's the power of a function. So all of those, kind of like substitution method. And then 1.3. 1.3 is for polynomial function and a rational function. We just direct substitute. And the theorem 4, radical function, again, we direct substitute. See, 1.3, 1.4. 1.5 is composite function, f of g of x, direct substitution. As long as the g of x is that value after you do substitution, then that value is in the domain of f, then you can go ahead and do it, okay? And 1.6, again, direct substitution method. We talk about the trigonometric function. Boom. 1.7 is if you have f and g, and they agree with each other except at one point, then they get the same limit at that point. So that's all these theorems of limit. We learned 7 of them. And also, most of the time, we just use the direct substitution method. Okay, so that is all for the first part of this session.